All right, welcome. Today we are diving into something huge. And I'm not talking about physics like it's some boring subject you had to take in school. No way. We're talking about it as one of humanity's oldest, most incredible quests. The attempt to understand, well, everything. So, with a topic that big, where do we even begin?
Well, let's start with a question. Think about this for a second. You've got a bolt of lightning tearing through the sky, a galaxy spinning millions of light years away. And the smartphone that's probably in your hand right now? What on earth could possibly connect those three things? The answer, the single thread that weaves them all together, is physics. It's like the hidden blueprint for the entire universe.
So to really get a handle on this, let's start with the basics. What is physics really? The best way to think about it is as our ongoing mission to discover the fundamental rules of the game. And the game, in this case, is the entire universe.
Okay, so here's the more official definition. At its absolute core, physics is the study of matter, energy, and how they interact with each other across space and time. It's our most fundamental shot at looking at nature, breaking it down, and figuring out the deep principles that make the whole thing tick. It's the how and the why behind reality itself.
And this quote just perfectly illustrates how foundational this all is. The legendary physicist Richard Feynman said that if some catastrophe wiped out all scientific knowledge and you could only save one sentence, the single idea that all things are made of atoms would be the most valuable. I mean, think about it. That one simple concept, that everything is just made of tiny, jiggling particles, that's the starting block for understanding pretty much everything else.
But here's the thing. This quest didn't just kick off a few hundred years ago with a bunch of guys in wigs in Europe. The search for how the universe works is a truly global story. It's a human story, with roots stretching back thousands of years and across every single continent.
And what's so cool about this is just how widespread this curiosity was. We see evidence of people in Africa making astronomical observations over 25,000 years ago. You've got philosophers in ancient China running experiments on light and motion. In India, a whole school of thought came up with a really sophisticated theory of atoms. This stuff is in our DNA. And you cannot tell this story without talking about the Islamic Golden Age. A scholar named al-Haytham did something that was an absolute game changer. He didn't just sit around and think about how light works. No, he tested his ideas. He ran experiments using tools like the camera obscura to get actual proof. He helped build the very foundations of the scientific method that we still rely on today. All right, so this brings us to an era that's probably a bit more familiar, what we now call classical physics. You can think of people like Isaac Newton as the ultimate code breakers. They were the ones who finally started cracking the code of the world we see every day, revealing these beautiful, predictable laws.
And these were the main pillars of that code. You had classical mechanics, which gave us the math to predict the motion of everything from a planet to a cannonball. Then came thermodynamics, explaining heat and energy. And then James Clerk Maxwell came along and unified electricity, magnetism, and even light into one elegant theory of electromagnetism. For a little while there, it really seemed like we'd figured it all out, that the universe was just this perfect, predictable clockwork machine.
But, as it turns out, that beautiful clockwork picture wasn't the whole story. See, classical physics is fantastic for our everyday world. It works perfectly for baseballs and bridges and planets. But the moment physicists started to poke around at the extremes, at things moving near the speed of light, or things as tiny as an atom, the rules just fell apart.
And right here is where our story gets a massive plot twist. Around the turn of the 20th century, a whole series of baffling new discoveries showed physicists that the universe was, well, it was a whole lot weirder and way more wonderful than anyone had ever dreamed.
I mean, can you imagine the feeling? This elegant, perfect system that had been built up over centuries just stopped working. The neat and tidy rulebook that explained everything so well suddenly had huge gaping holes in it. It was clear that a completely new kind of physics was needed.
Part of this new reality was realizing just how much of the universe is completely hidden from us. Take a look at this, the electromagnetic spectrum. You see that tiny little sliver of rainbow colors in the middle? That's visible light. That's every single thing a human eye has ever seen in all of history. But look at all the rest of it. Radio waves, X-rays, gamma rays, it's all the same stuff as light, just different wavelengths our eyes can't pick up.
And to put the scale of this into perspective, it's just mind-boggling. Some radio waves are literally as long as a building. On the other end of the spectrum, gamma rays are so tiny, they're smaller than the nucleus of a single atom. We are swimming in an ocean of energy and information that we are completely blind to.
So what were these new, bizarre rules? Well, they came from two revolutionary pillars. First, you have Einstein's relativity, which rewrote the rulebook for the very big and the very fast. It taught us that space and time are not separate things. They're woven together into a single fabric called space-time. And gravity? It's not some mysterious force. It's just the shape of that fabric being curved and warped by mass, kind of like a bowling ball on a trampoline. Then you have quantum mechanics, the rulebook for the super tiny. And this is where things get really weird. It tells us energy comes in little packets called quanta. This leads to mind-bending ideas like wave-particle duality, where something like an electron can be a solid particle one moment and a spread-out wave the next. And then there's the famous uncertainty principle, which says there's a fundamental fuzziness to reality. You can know where a particle is or where it's going, but you can never, ever know both perfectly at the same time.
Now, I know what you're thinking. This all sounds incredibly strange and abstract, and you're right, it is. But here's the kicker. This weird physics is the foundation of our entire modern world. Understanding the atom led to nuclear power. Understanding quantum mechanics gave us the transistor, which is the tiny switch that powers every computer and smartphone on the planet. And without understanding relativity, your GPS would be useless.
So all of that brings us right up to today, because this grand quest is so far from being over. In fact, you could say that all we've done so far is explore the foothills. The biggest, most profound mysteries are still out there waiting for us.
Right now, physicists are on the hunt for an even deeper set of rules, something they call a theory of everything. Ideas like string theory are basically attempts to find one single, elegant idea that explains all the forces of nature, from gravity to quantum weirdness, as just different notes played by a single, fundamental string. And the list of things we don't know is just breathtaking. We've figured out that most of the stuff in the universe is made of mysterious dark matter and dark energy, but we have basically no clue what they actually are. We still haven't figured out how to make Einstein's theory of gravity play nice with the strange rules of quantum mechanics, and some theories even suggest there could be extra, hidden dimensions of space all around us.
So, we end up right back where we started. Physics is the search for the rules of the game. We've found some absolutely incredible ones, but we know for a fact that our rulebook is incomplete. The quest goes on, driven by that same deep human curiosity that started all those thousands of years ago. Which just leaves one big question, doesn't it? What fundamental rule about our universe are we going to discover next?